acclimatized you to MIT. I'm Tom Eager, and I came here as an undergraduate in 1968. Got my doctoral degree here, worked with Bethlehem Steel Corporation for almost 2 years, came back as a faculty member, and been here 1 year. I've been here ever since, except for 1 year, which I spent my first sabbatical in 1984 to 85 in Tokyo, Japan, with the Office of Naval Research, U.S. Office of Naval Research. So far as that goes. Okay, so I sent around a sign-up sheet, and even though I have this sheet from the registrar, which lists 10 of you plus, actually, are you in that 10?
I don't appear to be.
Okay, see, that's why I'm sending around a sign-up sheet. So it's on a little metal pad, so you should sign up. But there are supposedly 2 other non-2N students, maybe 3. We don't. Well, a number of them inquire about it, and then when they find it 75, 45 of them work. In fact, I've had 2N students. I had one student one year who had to get his children off to school, and so he took the whole course by video. You don't have to ever come to class in this course, except to make your presentation. And that's one of the requirements. I'll get to it in a little bit. And you are?
Adrian.
Okay, Adrian, and are you in 2N?
I'm in SDM program.
Oh, SDM. Okay, you're the one who met with me yesterday.
Yes.
Okay, so I was explaining a little bit about the course. It is videotaped, and so if it's hard to get to class, you can take the class. You can take that lecture by video. Okay, it'll be posted on YouTube, and Young will tell everybody how to do it, or the other 2 people who are setting up for this. Stellar, which is the MIT course website, they hadn't even started to do it for the summer as of last Thursday, so there's a bunch of handouts. I used to give out hard copy handouts, but SPAC basically, I gave them some things to give to you and last week, and he said, well, don't you have a digital copy? So you'll get things digitally. I guess I'm just an old dinosaur still does things with Xeroxing. So you need to sign up for the course. The requirement of the course is to either watch the lectures or watch the videos. And in order to get 12 units, you need to watch, this is just like the MIT regular courses, about 36 hours worth of lectures. Okay? And here's the schedule. Since you don't have any other requirements, I'm going to hand out some things for you to read, and you can read those in your spare time. But the way we do things at MIT is Monday, Tuesday, Wednesday. Thursday begins with an R, and F is for Friday. So here's the dates, and we're here today on June 8th. And the schedule we worked out is that in general, well, actually I can come down to this week of the 15th, on Mondays, Wednesdays, and Fridays, except this Friday, I'm going to be out of town. We would meet for 1 hour till 8:45, actually probably about 8:40 or so. So anyway, on Tuesdays and Thursdays, we will meet for 2 hours. I'll give you a break in the middle of that, but it turns out this Thursday and the next Thursday I've got something scheduled, and so we'll only be meeting for 1 hour. I need to lecture about 8 or 10 hours, depending on what we do, maybe 12 hours, and you need to make a presentation, okay, each of you, and we could probably do 2 or 3 presentations in an hour, okay? The presentation can be on anything you want. Now I think, you don't, Andre, you haven't heard, most of the students who are here are in the U.S. Navy program, Navy officers. They come back for 3 years to get 2 master's degrees and other things. And in fact, it's sort of a plum assignment for Navy officers in the sense that there used to be about 10 universities across the country where the Navy would send back their officers. Just like you're in SDM, what company do you work for? Are you
Boeing.
Boeing, okay. So you're in the aerospace business. Well, same thing. The Navy just sends people back, just like Boeing sent you back, and they send them back to learn new skills and go back. Because they're actually doing the same type of, in fact, a lot of them are going to be in the How many of you have already decided you're going to be in the SDM program, Systems Design and Management? Typically, about half to 3/4 in recent years of the Navy students go into the SDM program during the 3 years and get an SDM degree. Andre is in the SDM program. You want to tell them about what the SDM program is?
Sure. It's about a 3-term program. It concerns, the name is System Design and Management, and it primarily focuses around engineering professionals that have about 8 years experience coming back to focus on system architecture, project management, and system engineering. So it's a unique program in that you take some courses from the business school from Sloan, and you take some from the engineering school that you kind of tailor based on what company or field you're going to go back to.
Right. Okay, so it turns out it's almost perfect, except the 2N program already existed before SDM was created about, when was SDM created? About 95, okay, or 94, 95. But the Navy program goes back 120 years. There used to be 10 or 12 universities in the country. There are now 2. There's the Naval Postgraduate School of Monterey, and there's the MIT program. There used to be 4 or 5 that had a Navy nuclear degree. MIT was one of, Penn State, Michigan, University of Michigan, I can't remember the others. But they've all, with budget cutbacks, they've all gone away except this one, okay? And Monterey is always trying to kill this program. I've been to meetings in Washington for 30 years about whether they're going to keep the 2N program at MIT. And the Navy brass all decide they want you. And so one of you said before class, everyone else I said, how'd you get this assignment rather than Monterey? And Monterey is pretty nice weather, folks. I mean, let's face it, okay? But this is the plum assignment. And you really are here because you're the best, okay, that the Navy has to offer. Pretty frankly. In any case. And you're the best that Boeing has to offer, okay? I mean, people who've gone back to Boeing from this program have headed up, ended up a couple of years later heading up the building of a new aircraft, okay, for the whole program, okay? And some of you will head up building a whole new ship, okay? One of the first people I met in Washington was Millard Fireball, who Millard was a captain at the time. He was head of the SSN-21 program, okay, with the Seawolf submarine in the 1980s, when it got canceled by Congress, okay? And then he had to go up to the hill. He got reinstated. And then when the Seawolf had a problem, boy, this is getting to the point where some of you were barely born, but nonetheless, Seawolf had a problem that ended up costing the Navy $2 billion. And at that point, Captain Fireball, who was a graduate of this program, before my time, because he's older than I am, but Captain Fireball was then Admiral Fireball. He was chief engineer of the Navy. And he put me on a committee with a bunch of other people to figure out what went wrong down at Electric Boat. And why they had cracks in all their wells. Okay, we'll take a little break. We'll set the thing out, set up some food, you can start your breakfast. Well, I'll keep this schedule, and it'll be modified as time goes on. But we meet every day that we can. We also, in the Navy, the Naval Sea Systems Command tells you that you have to take a welding metallurgy course, and a welding course, and a corrosion course. And this sort of fulfills many of those. For those of you who are not part of the U.S. Navy, or if you're Canadian Navy or Coast Guard, you may have a choice. You can check with whoever your supervisor is. I'll pass these around to those of you that are not in the 2N U.S. Navy program, because these are the other 36 units, or the other 24 hours of lecture that you can take if you like. For you guys that are in the 2N program, the decision has been made for you. You will take this module that I'm doing this summer. You also take the solid state welding and fusion welding, which I've highlighted, and this will get posted on Stellar. But these are, if you go to my website, eager.mit.edu, here, okay, and you you go to classes, you'll see this list, and these should all have a link now to YouTube videos, and you can watch a prior year's lecture, okay? Now, your assignment is to give a presentation, as I said, and the presentation should be 10 minutes long, means a PowerPoint of no more than 10 overheads on PowerPoint. It can be on any subject you like, but to give you an idea of what the 2N people last year did, one student did flight deck corrosion. And a lot of these things are things that you may have already done at a shipyard or on board ship. I was telling Spack that 1 year after the, I think it was the second Gulf War, which only lasted, what, 3 days or 2 days or something. Anyway, there was a destroyer in the, what do you call that bay there? Persian Gulf, okay? In the Persian Gulf, that was part of the attack, and all of a sudden their 3,000 psi air system went out on the ship, and if you lose your 3,000 psi air system, not much else works. And so they had to come offline in the middle of the attack. People in the Pentagon were not happy, and it turns out it was a stress corrosion cracking problem in a brass valve that blew, and they lost their pressure. And it turns out, so this one student who had been on board that ship gave his presentation on this experience they had. And it turns out another student in the same class, and they didn't know that both of them had worked on different parts of this. The other student had been at the Naval Supply Center in Philadelphia, and after this occurred, they went and had to study everything they had in inventory because the brass alloy was the wrong alloy. And they found like 20-some% of all the brass valves in the supply center, not just this type, but all of them, were the wrong brass alloy. Okay? And so, so both of them were kind of working on different parts of the same problem. But anyway, one student did flight deck corrosion, another one did replacing Monel in submarine piping with titanium, another one Monel weld metal on stainless steel, another one did a bearing failure they were familiar with, another one did new ship construction, one was a Navy nuke, and he did nuclear corrosion from a generic point of view because he felt that anything he knew about Navy nuclear must be classified. Okay, that's not true, but nonetheless. So anyway, you can be on corrosion, you can be on welding. I've had students talk about sailboat masts, okay, so far as that goes. Any topic you want, because if you pick a topic you're interested in, you'll do a better job. I've had a number of students essentially do a presentation of what they had to present right before they left the last assignment. Many of you have had to do presentations, and I don't care if you use it. I've had, when undergraduates take this, some of them will do something they did for their summer internship, okay? Doesn't matter to me. It's not that I'm trying to make you work hard. MIT requires that I evaluate each student independently, okay? Can't evaluate you as a group. I have a very bad attitude about teaching. Having been a student here and having taught here for a number of years and looking at how we teach in general in this country, we teach so that students can pass exams, okay? We don't teach so students can learn. We train you to take a quiz. And I'm of the opinion you wouldn't be here at MIT if you didn't know how to take a quiz, okay? You never would have gotten here. So therefore, I'm not interested in testing your ability to take a quiz. I'm not interested in writing the quiz. I'm not interested in grading the quiz. The students will say they learn more from the students' presentations, or not necessarily, they don't say they learn more. They say they enjoy the students' presentations as much as the lectures. Okay, how about that? I learn more from the students' presentations than from the lectures because it's sort of assumed that maybe I knew what I was talking about in the lectures. I would much rather that you interrupt me in the lecture and ask a question so that I can digress on something else. That's the challenge for me, whether I have a story to tell about your question. Okay? And students are usually pretty surprised to see the breadth of my stories after 40 years in business. And I'd rather tell the story because I've never heard these lectures, guys. I mean, after a while, after you've taken the class 20 times, it gets to be kind of old hat. Okay, you haven't taken it 20 times, but for me, anyway. So you're supposed to take 3 modules, and for the 2N students, it's solid state welding, fusion welding, welding metallurgy / corrosion, which is what we'll be doing. We talked about breakfast. Part of this is also adjusting to MIT. Were any of you MIT undergraduates or graduate students before? No? The class that just graduated had, she's probably Commander McCoy, but she was the leader of the class, okay, as more senior. And she had gotten a degree in aeronautical engineering from MIT as an undergraduate. So she was the only class of 30 years I've been doing this that I didn't have to help the class adjust to MIT. And many of you may have already heard getting an education at MIT is like taking a drink from the fire hose. And it's not a bad analogy. But in fact, MIT's not really, well, it is that intimidating, but it's not that bad, okay? 95% of all the pressure at MIT is self-inflicted. Doesn't matter whether you're a student or a faculty member, there's a lot of pressure around here, okay? So you need to learn to adapt to the pressure. And I actually gave back this should get posted on Stellar, but I gave him a copy of this article I wrote a number of years ago, 10 years ago, for the MIT faculty newsletter on leadership, management, and education at MIT, trying to tell what I learned at that time over about 36 years at MIT of what makes MIT unique. One of the things that makes MIT unique, not completely unique, but Caltech and MIT are somewhat unique in the sense they only admit 1 class of students. Anybody know what the class of students is? Scholars. So some of you read the article. Okay. Whereas Harvard and the other Ivy League schools, Princeton, they admit scholars, athletes, and legacy students, okay? And you can always compare yourself to a legacy student because most of them probably shouldn't have gotten out of high school, but they great hockey goalie or whatever. But at MIT, you have no one to compare yourself with like that, and on average, you're average, and so I'm just kind of telling you what you've already read. But MIT is not, well, I shouldn't say, it is as intimidating as you hear, but it's not really that bad, I guess is the way to say it. And other people made it through, so why shouldn't you be able to, right? Okay, but there'll be times, you know, I think I told the story in there about freshman year when I thought I was going to flunk freshman physics, okay? I don't think I told the story in there about junior year when I had my epiphany. And I was taking Introduction to Quantum Mechanics in the physics department. I was a materials student. Why I decided to take quantum mechanics, I don't know. But, and I had a good teacher, Vera Kostякowski, full professor of physics, one of the first 2 women to get full professorship at MIT. Her father was a Nobel laureate at Harvard in chemistry. Brilliant woman, nice person. I didn't follow a thing she was talking about in class. I was getting 15s out of 100 when everybody was getting 85 out of 100 on the homeworks. And had a 3-hour final, and the night before I just said, okay, I'm going to take Iceberg from the Fundamentals of Modern Physics and just go through and pick out the highlights. And I did. And I went into the 3-hour exam. I finished it in 1 hour and 20 minutes. I had to wait for another 20 minutes. I checked it over and walked out of the class. I got an A in the course. Okay. And all of a sudden, the light went off, and I said, "Oh, all that other stuff they talk about, it's just fluff." Okay. And I realized they can only quiz you, or they can only get 2 or 3 points across in an hour. Okay? And if you could figure out what those 2 or 3 points were, that's what the quiz was going to be on. And from there on out, I just aced MIT. I didn't take notes, okay? I just sat there trying to figure out what was this professor's outline? What was he trying to tell me, okay? And a lot of anything in life is trying to figure out what the problem is. I've given you some other handouts that will be on Stellar. One's an article I wrote a couple of weeks after the World Trade Center collapsed, which for about 8 or 10 years was the #1 article if you looked up Google WTC collapse. And the reason it was the #1 article is I was asked by an editor to write it. I was so sick of hearing such false information like the steel melted in the fire. Anyone who's ever been to a fire knows the steel doesn't melt in the fire, okay? If steel melted in the fire, we didn't need Sir Henry Bessemer in 1856 to teach us how to melt steel. We would have been melting it for a few thousand years before that. But I wrote this in 3 hours, which is less time than it took for me to write any of my several hundred publications. I got more comments on this, positive and negative, than any paper I've ever written, or actually all of the papers combined. Why? Because I wrote it for a high school science student. I was trying to write it so someone could understand it. And that's one of the things that I learned about almost 30 years ago when I took the Sloan School subject, actually Sloan Senior Executives Program, and I heard this guy, Lester Thurow, talk. He was the dean of the Sloan School, and Lester he called himself an educational economist. Now his colleagues at the Sloan School called him less than Thurow. Okay? But Lester was getting, this is 1988, he was getting $30,000 a lecture. Not quite as good as the Clintons are doing right now, but that was still pretty good back then. And he had the #2 top-selling book in the New York Times book list. And as he once said, never try to compete with the Princess Diana's book. Okay. He was #2. And but it wasn't what Lester said. And when I took this senior executives program, Lester came in twice to talk to us. He was just an engaging speaker. You just loved to listen to him. It just seemed to make so much sense of what he said. And we were all the first time I had ever heard of him, and I was impressed. The second time he came in, everybody else there, these other 49 senior executives in the industry, and I was the one academic in the room. They were all just enthralled to hear him again, and I was sitting there trying to analyze what he said and why he was such, I wouldn't mind getting $30,000 for a lecture, right? If you guys start figuring out what your tuition is, actually, MIT is getting about $30,000 for this lecture. Well, not quite that, but $10,000 probably. You start adding up the tuition, the number of hours taught. It's pretty impressive. Anyway, and at the end of what Lester said, I realized he didn't say anything I didn't already know, but it was the way he said it. Okay? And so I changed, by 1989, I changed the way I was going to conferences and giving talks. And for example, I was talking about welding. I was giving a keynote lecture in welding on resistance spot welding, which is how they put automotive bodies together, at a conference in Gatlinburg, Tennessee. And I said, you know, they put 3,000 spot welds in the average automobile because you need 2,000 good ones. Okay? And a year later, I was at the Welding Society conference at a reception, and I heard someone behind me saying, you know, they put 3,000 spot welds in the average automobile. People will remember short little quotes, okay? We live in a soundbite world. My favorite quote from Lester was a few years later. He was dean of the Sloan School, and he was giving a lecture over here at the Marriott Hotel to a group of people, alums and stuff. And he was lamenting the fact that we tend to lose some of our best faculty to other universities who pay big bucks for them, okay? And everyone kind of knew he was talking about Robert Merton. You might know who Robert Merton is. Robert Merton was the guy who worked with Black and Scholes on derivatives. You've heard of derivatives? And I'm not talking about, you know, EDX, DX. Okay, I'm talking about derivatives as trading on Wall Street. It's called the Black-Scholes method, but Merton was the postdoc or whatever working with these two faculty. And they came up with this way to predict the value of the price of stock in the future in a very precise mathematical way, okay? And now this led to the whole derivatives trading, which led to the collapse of the economy in 2008, okay? They have a bunch of people in Wall Street are sitting around the table placing bets with each other, okay? Actually, they call it selling the risk, okay? Trading the risk, but every time this person who owns $5 billion worth of mortgages says, I'll sell you 3 billion of these, but you're going to have to give me, 2% or whatever for, I'll give you 2% for assuming the risk. And they just go around in a circle and keep trading paper going around in a circle. No value added, okay? And everyone is getting a cut of the action on trillions of dollars. The amount of derivatives in like 2004 in the world was $1 trillion. The amount of derivatives in 2008, at the time of the collapse, was $50 trillion. It's equal to the world's gross domestic product for a year. And what happened is the banks, when a couple of them defaulted, they were going to have to pay another bank for their default, and they didn't have the cash, and the other bank was going to have to pay the other guy sitting on the other side of the table, okay? And they didn't want to give up their cash. It was just like the stock market crash of '29. Everyone wanted to hold on to their cash, and no one, because they were afraid that someone was going to call them on their paper, right? So anyway, he was talking about Robert. He didn't say Robert Merton, but everyone kind of knew. But Merton had been a faculty member at Sloan. He got hired away for big bucks to Harvard, and a couple of years later, he won the Nobel Prize. Okay, Bud Blackenschulz passed away. But anyway, so Merton won the Nobel Prize. Lester's lamenting the fact that some of the star faculty are hired away, but he says, but fortunately, they tend to hire our extinct volcanoes. Okay? Now think about it. He didn't have to explain to anybody in the room what he meant by an extinct volcano in that context, right? And so you need to learn to communicate in vivid metaphor soundbites, okay? Because that's what the management at the top wants to hear, folks. Sorry. Another article that you'll get is Materials Research Needs in the 21st Century. And this is an article right here that I wrote for this National Research Council of the National Academies Committee. They had a committee of people from around the country trying to tell the Defense Department what materials, high-tech materials they would be using in the 21st century. This was copyright 2003, so we were doing this around 2000, 2001. And if you look in the beginning, it gives the names of a lot of distinguished people. Harvey Shatter was chair, General Electric Research. Alan Lovelace, General Dynamics, retired. James Baskerville, Bath Iron Works. Okay, I think he was a graduate of this program, 2A program, I think. I know Jim Millard Firebaugh. Okay, this is the one I talked about. He was electric boat then, but he's been chief engineer of the Navy. Anyway, there's a lot of distinguished people trying to divine what materials people would use in the future. And I didn't really fit in there because I tended to agree with this $1 million U.S. Army study. The U.S. Army had done a study in the late 1990s of what material the U.S. Army would be using the most of in the next 30 or 40 years. Anybody know what it was? It cost them $1 million to figure this out. Steels. Steel, not humans. The good news is that's actually, I said, use humans. Anyway, it's steel, okay? And I'm going to tell you why it's steel in a moment. But because I couldn't convince them that it would be steel, and they needed me to write something, I sort of took the outline of my material selection course, which is one of the modules of 12 units, and I put it into this 4-page summary, which they put into an appendix in there. That's so it doesn't have my name associated with it. That's fine. I'm not ashamed of it. In 1992, I wrote this article in the Welding Journal called The Future of Metals. This was at a time when people thought fine ceramics were going to take over jet engines and everything else, and they didn't. And I was predicting in 1992 that they wouldn't. And how did I know this? Anybody know how I knew this? Because I was looking at the properties of these materials. What if you think of a ceramic, what do you think about as a structural material?
Hard and brittle.
Hard and brittle, right? High temperature too, which is why they wanted it for jet engines. And they actually built jet engines. But it turns out the critical flaw size for a brittle material is extremely small. Okay, it's a very simple formula. The toughness has to be greater than the stress times the square root of pi times the crack length. Okay? Well, this is the applied stress. You can get a very high applied stress. The toughness of a ceramic is terrible. Okay? The crack length. Anyone ever seen someone cut glass? What do?
Score it.
They take a carbide or a diamond tool and they scratch the surface. And they can make a wavy cut, straight cut, whatever they want, and then they can hit it with the heel of their hand, and it'll just break right where they put the scratch. Because the critical flaw size is less than a human hair for a brittle material like glass. So as long as you make a jet engine with no imperfections in there, larger than half or 1/10 the size of a human hair, it'll run at great temperatures. And you know, we've already done that. It's called a cruise missile. Okay? The cruise missile engine is made out of graphite. Graphite's not particularly tough, but it only has to last for an hour. And the bigger problem is keeping it from burning up in an hour. They have to put coatings on it and stuff to keep it from burning up. But it doesn't have to last that long. And in fact, graphite's tougher than most of the ceramics. So I used to say, when I was in Japan, in Tokyo in the mid-80s, they had what they called ceramics fever. And at Shinjuku, if anybody knows, some of you know what I used to post it, he said, Shinjuku is the world's largest subway station. My son is now in his 40s, actually he called me up once in 1984. While I had gone to Australia, he had gone to Mount Fuji with some scouts to climb Mount Fuji. And I'm sitting there eating dinner after I got home about noon from Australia. And I get a call and Matt says, "Dad, can you come pick me up?" I said, "Sure, where are you?" He says, "I'm in Shinjuku." I said, "It's the world's largest subway station. About 2 million people a day go through there. It stretches for about 5 miles, okay?" And I said, "Well, where are the people you came with?" "Oh, they're going down to Shibuya," which is several subways. So I said, "I'll meet you at the Dog." That's where all the gaijins, the foreigners, would meet at the Dog in Shibuya because they have this statue of the dog. Okay? And so I said, "I'll meet you at the Dog," which is only 3 subway stops for me and about 4 for him. So I didn't lose my 10-year-old son. I had dinner with him last night. But in any case, on this
You're talking about graphite engines.
graphite engines, right. So they had a ceramic, they had a ceramics fever, they call it ceramics fever in Japan. They had a ceramic show when I was there when I left in 1985. 1 million people showed up. So this is not just your scientists. Everybody thought fine ceramics were great, and they were going to take over the world. And I came back, and I used to give talks at NIST in Gaithersburg, Maryland. I remember the big lecture hall, and I got up and I said, "Well, the problem with ceramics is they don't have any toughness. In fact, the only materials that are made out of ceramics, structural materials made out of ceramics, are Portland cement and toilet bowls. And I throw in the kitchen sink, but you got to line it with cast iron to give it fracture toughness. Okay? If you drop something in the sink and it was just made out of ceramic, you'd end up with a shattered sink. So they have to make it out of cast iron. And gray cast iron is the worst metal of all, okay, in terms of toughness. So people forget this toughness requirement. We're going to talk about that some more, okay? So I knew it was going to be, well, actually, I'll put it up right now. Got several things here to show you. If I look at all metals and other materials, this comes out of Mike Ashby's book. Professor Ashby was at Harvard. Now he's retired from Oxford, but he's British. He's a great scholar. He wrote a book on material selection and mechanical design. If you wanted to take, if I had to recommend something for you at Boeing to take, if you're not already a materials person, there's a material selection module, which is one of my favorite modules. although you're gonna hear me talk about steel all the time, okay, just like I'm gonna talk about here. This graph came out of there. Ashby came up with these things that are now known as Ashby plots. This is fracture toughness versus strength. For a lot of classes of material on a log-log scale, you can plot anything on a log-log scale, right? And get a straight line, except these aren't straight lines. Here's the fracture toughness. K1C squared over pi times sigma squared. So this is basically the critical crack length. And if this is in centimeters, 100 centimeters would be the critical flaw size. That's pretty big. Except the only materials that will cross that line are some of the engineering alloys, and steels are right up here. What you want is the highest strength and the highest toughness. So up here at 45 degrees, you want everything that's going to be at the top of this, and that's where steels are. Along with nickel alloys, titanium alloys, copper alloys. Aluminum alloys are way down here. Engineered ceramics are down here. Critical flaw sizes of 10 to the minus 3 centimeters? That's less than a human hair. Okay? So ceramics are great, as long as you load them in compression. And that's what we do with Portland cement. Okay? So polymers, they're down here. So actually, I'll do it for you tomorrow. I don't have time right now to make this big graph that I done this morning. Is another way to think about looking at this. But if you look at material selection, it turns out there's a reason why we use metals. And that's because they're ductile. They have the ability to deform under load.
Real quick,
Yeah.
I don't know what it means to load something under compression, like for cement, for instance. What does that mean?
3,000 PSI.
Practically, what does that mean?
Okay. Well, first of all, Portland cement, you add water to it. You start with limestone. You put it in a kiln. You drive the CO2 off. You make burnt lime, which is calcium oxide, magnesium oxide, a bunch of other things. You throw some sand in, which is making a composite out of it. And you mix it with water, and the water hydrates the burnt lime, calcium oxide, to, could be magnesium oxide, plus H2O gives you calcium hydroxide. Now this is a way oversimplified formula for This is a way oversimplified formula for the chemistry of Portland cement. But basically, that's what it is. And it takes time to set up. And it actually gives off heat when it sets up. If you put this, if you pour Portland cement and you just go stick the thermometer in it, 5 hours later it'll be about 140, 150 degrees Fahrenheit. Okay? It's exothermic reaction to do this. It takes a month to get to its engineering strength. And so when they pour the foundation out here for the new nanotech building they're building, they will pour cores and they'll send them to a laboratory. And they may test them after 1 week, and maybe they have to support 1,000 PSI after 1 week because it hasn't finished setting up. But after 30 days, its structural design strength should be 3,000 PSI. And if it fails after 30 days, rip it out and start over. Okay? So does that answer, might be just beating around your question? Or
That tells me that you do load it to make sure that it's working correctly, I guess, to make sure that there are no, flaws in it.
But you only put it in compression. Okay? If you want to put it in tension, you have to use steel rebar. Here's a piece of steel rebar. It's got notches rolled into the surface so that the steel, the concrete grabs those, and that takes the tension. If you make a concrete beam, the bottom of the beam that's in tension, in bending tension, it's the steel that's taking the tension, not the concrete. Concrete may have 500 PSI tensile capability, but it depends on the size of the bubbles in there, things like that. Okay? The engineering credit you get for concrete and tension and the engineering design is 0 for tension and 3,000 PSI in compression. Okay? And you put steel in it. When they were just pouring some steps in the basement for this part of the nano lab, they had wire mesh for the steps. Well, steps, what do they do? They're mostly in compression. You only stand on them. You're not pulling on the steps. But yeah, there's going to be some area in there, even though it's on a foundation. But they still give it zero
I
pressure.
guess maybe a better question is, are you saying that concrete doesn't set correctly unless you compress it as it's curing?
No, I'm just saying it takes time to get to its strength. Just like epoxy. You mix 2-part epoxy. Concrete is 2-part. You take the dry Portland cement and you mix it with water. And then it forms a chemical reaction, and it takes a month or more to harden up. In fact, it can take years to harden up. The oldest reinforced concrete structure in the country is Harvard Football Stadium, okay? And if you go drill in that, or if you drill in the 1917 is here, okay, which is only a few years later, you go ask the workmen around here about drilling in these walls that are concrete walls. This stuff is really hard after 100 years of setting up. I mean, you have to have a hammer drill with a carbide tip and things like that, okay? So, So concrete is, oh, go ahead.
I was going to see if I can just try to that concrete is really, really good to resist being crushed. But it's very, very weak when being pulled apart. So you want to use it in applications that you're only crushing it, not that you're making it resistant being pulled apart.
You can't put it in tension. I had a case, Mike will tell this story, back in the early 80s. They were building a new building for Dan Rather for his union, or CBS, I think it was CBS. He was working for them. And they had concrete beams. A 6-story building in New York, in Manhattan, and they had concrete beams, and they had steel rebar like this. And during construction, like the 5th floor, one of the beams, which is there like this, in tension, just, not in tension, but I mean the bottom was in tension, it was in bending, compression on the top. That's fine for concrete. Concrete's great in compression, but it's lousy in tension. It broke, and it, like a house of cards or dominoes, all the other beams came down. One guy broke a leg, one of the workmen fell on and broke a leg. But otherwise, it was just like a $50 million loss or whatever. Plus, Dan Rather didn't have his nice news for another year. Okay, delayed construction and stuff. Well, I went out to the scene, I looked at it, and all this rubble, and you couldn't really tell too much. You couldn't really get on the other side because you'd be out in the middle of the air. Okay, these things were all into the floors. Well, finally, they had some inspection. I couldn't meet the day of the inspection because of some family vacation, so I had to go like 2 weeks later to this wood storage facility. It was CBS's property. They had to have some way to store this stuff while the lawsuit's going to go on. And I'm out there. It turns out the place they had was CBS owned Steinway pianos at the time. And so they have to season their wood, and they have big racks of wood. They're out there for 5 years seasoning. And right across from LaGuardia Airport, you look through the chain link fence, you see the runway, right 100 yards further down, okay? And I'm out there, middle of July. I'm looking down, and I'm looking at the fracture surface, the brittle fracture on the steel. And this rebar should not brittle fracture, it should bend before you break. You've been to a construction site, you've seen them bend rebar, right? It's not so brittle you can't bend it, because it's a metal. But this was a brittle fracture. And then I looked at this one, and it had concrete on the fracture surface. And then I realized, I looked at some of the others, they're still encased in concrete, but they had tack welded these things together where they crossed. You don't tack weld rebar. It's high carbon. It'll form a brittle fracture. That weld will have lousy fracture toughness. You'll drop it by a factor of 8. And so this tension connection was now a glass brittle tension connection at the toe of the fillet welds. Okay? Because the weldability of the steel was lousy.
Are you otherwise supposed to connect the rebar?
You wire it together. You take little wires and you wire it together. You make a cage. There are rebars that are designed to have high strength and low carbon for good weldability. But most rebar is garden variety merchant quality steel. Okay? And that was the answer to this case. And then I got a personal tour of the Steinway piano factory. And I now, when I see a Steinway, I go up and I start inspecting it to see all the different things they do for a Steinway, why it costs so much. A lot of good reasons. Really good craftsmanship goes into the Steinway. In any case, one of the points I'm trying to make is we use, and this is one of the 2 or 3 for today's lecture, is we use metals because they have good toughness. And we don't use ceramics because they have lousy toughness, they have lousy fracture resistance, their critical flaw size is so small that you can never inspect for those things. Okay? And it turns out the Seawolf submarine problem, if you want to get back for a Navy example, is the problem with the Seawolf submarine was they ended up getting too high a carbon content and alloy content. We're going to talk about some of this stuff when we get to it. But the weld metal was 30 or 40% higher strength than it was intended to be because of the chemistry of the weld metal. And they got a less tough steel that formed little microscopic flaws that the original inspectors weren't looking for something that small. It was a different type of cracking that we hadn't seen before. And they had built 18% of the ship hull before a guy found it, and he found it by a non-destructive test technique that was not exactly authorized. The outside of the hull has to be very smooth. They grind off the weld reinforcement because you want a hull that is so smooth that even the weld reinforcement will create enough of a ripple that guy listening on the other side could hear the noise from that ripple. Okay, so they have to grind the weld smooth on the outside surface. The guy was doing this. The grinder was grinding it, and he saw some of the grinding swarf. What's grinding swarf?
Leftovers.
Pardon me?
Leftovers and they're smoothed out.
Yep. Good Scrabble work for you folks. Okay? That's swarf. Okay? Grinding swarf is the little powder you can get from grinding. And he noticed some of it, which had been magnetized by the fact that you can magnetize steel just in there as a magnetic field, was aligning with these little cracks in the weld metal. And he had never seen that before. And he had enough sense to call over and inspect and say, what's that? I've never seen that before. And so then they went in with their instruments and they found these things that were about 1 millimeter in size. And typically, all the requirements for any inspection anywhere, except some of Boeing's, okay, which are tighter than anything that the world ever needed. We can talk about that. I got a good story on that. Typically, we're looking for 1/8 of an inch, 3 millimeter flaws. And these were 1 millimeter flaws. They were all over the place. But they were very small flaws. Okay? And so, this guy saw that they went in and they did the inspection and they realized all the welds in the submarine and they had to cut out every weld. Okay?
What testing do they usually do for those?
They typically do a magnetic particle, but they're looking for large flaws. And typically, if your minimum detectable flaw size is that 1/8 of an inch, reliably detectable. Actually, the Air Force did a bunch of studies in the 1980s on what they call probability of detection. Okay? And if you plot the probability of detection by flaw size, and I'm plotting this in inches now, because that's what we use in this picture. And this is 100%. You find the curve looks something like this, and you'll be at 95% probability of detection by a manual inspection, okay, at 1/8 of an inch. You'll be at about 50% at a 1/16 of an inch. These were down here in the millimeter size. Very low probability of detection. Aircraft engines, they're looking for things 15 thousandths of an inch. We don't really have inspection technologies that can do it. And Boeing has specs of 10 thousandths of an inch. Okay? No one can find it, but it's in the spec. Okay? I can tell you that straight.
So if it's not detected, it's not there, right?
Pardon me?
If it's not detected, it's not there, right?
That's right. You better make sure that you've designed the structure so to tolerate a flaw that size. Well, actually, I'll tell you this story since we've only got a couple of minutes left. So this was late 80s. They were coming out with the 747-400. So we dated by that. And to get this was an extended range aircraft of the old 747. And they had switched all the air tubing from stainless steel to titanium to save weight. And it turns out Engelhard was building the catalytic converters for the air you breathe. Why do you need a catalytic converter on a high-flying aircraft? You know? Sitting here in the security part. Because there's a lot of ozone up there. You know what happens if you breathe a lot of ozone for 8 hours or 3 hours on a flight? You get terrible headaches. Ozone is not good for your health. It's good for cleaning smoke out of a hotel room if someone's smoked in there before you. But ozone is a strong oxidizer, and there's a very low tolerance level, and there's all kinds of ozone up in the atmosphere. And the air that's coming in is what the passengers are going to breathe, so you have to put it through a catalytic converter to scrub out the ozone. And so just like the catalytic converter in your car, there's these great big catalytic converters for all the air coming into the aircraft. Okay? And they were replacing this with titanium to cut down on the weight on the 747 so they could make it a 10,000 mile aircraft or something. Some of the aircraft are now like 13,000 miles. And why don't they want to go any further than that?
Too old, it's too heavy.
No. You get halfway around the globe with 13,000 miles. Get anywhere you want. The only people who want 25,000 miles for an aircraft are the U.S. Air Force. And I was on a committee once. Actually, it might have been this committee. I don't remember. It might have been a different one. No, I think it was a different one. I said, why do you need 25,000 miles? You can get anywhere in the globe with 13,000. He said, we are planning in the future not to have a base anywhere in the world other than the United States. And if you look at it, it's probably not a bad planning exercise. I'll tell you another story. Actually, this one Millard Farbach told me. He said he was at the Pentagon once when he was chief engineer, and the Air Force was some Air Force general, major general or full general or whatever, was complaining about the cost of aircraft carriers being $15 billion. And it turns out the cost of a U.S. Air Force air base is also about $15 billion. Okay? And Millard, and so this Air Force general was at this meeting of the Joint Chiefs or whatever it was, and he was complaining about the cost of aircraft carriers, because obviously he probably wanted some of that budget the Navy had. And so Millard says, well, you know, I served in Vietnam, and I don't remember leaving a single aircraft carrier behind. That's actually one of my favorite quotes. I often tell people, we're not going to leave anything behind, okay? That comes from Millard's quote about leaving things behind. I guess I can give you some demos of ductile behavior. This is a piece of polyethylene plastic. This is ductile. This is plexiglass. And that's the, which would you rather fly in, or go over the waves in the storm in, or go under the ocean when someone's dropping depth charges at you? Okay? The Navy designs submarines for perfectly plastic behavior. Okay? Costs a fortune. Surface ships are sort of somewhere in between these two. Okay? Airplanes, well, they're actually this. Okay? But aircraft get a lot more inspection. We do a lot more things with them. The other example I give of toughness, which I guess we have, I'm actually going over with this. You have classic 9, right? The other example I give of toughness, and I actually have done this on the History Channel and some other things. A brittle material, well, you can talk about the strength of the material. It turns out paper is brittle. But you can pull on this without a crack with several pounds of force. But if I put a notch in it, it takes ounces. And it's brittle. I can tell it's brittle because when I put it back together, just like a cup that I drop, I can glue it back together. Everything fits perfectly. If I have a ductile material, one of the most ductile materials we know is rubber. This is gum rubber. I can put a great big crack in that, and all it does is blunt itself at the tip. This is a piece of other rubber that I pulled for many years. Pull this as hard as I can barely extend it. Okay? So that's the difference between strength and toughness. The reason we use metals is because they have excellent strength, excellent ductility, and it's not the same, but it's somewhat related. They have excellent toughness compared to any other material. Now, some polymers, I just showed you polyethylene, has excellent toughness. Why don't we use polymers?
No strength as well.
They don't have enough strength, but they also don't have enough temperature capability. Most polymers poop out in hot water. Okay? So polymers are fine at room temperature. But if you need anything to go a little bit higher than room temperature, you're not going to use polymers. Certainly not anything above. Silicone polymers can go up to about 500 degrees Fahrenheit. Okay? But if you need to go to 1,000 degrees or something, it's going to be metals. And you only got choices between metal, ceramics, and polymers. So we talked about broad classes of materials. So we're going to talk about metals, and specifically we're going to talk about welding. And I'll see you tomorrow. A couple hours.
Brexit all right?
Yeah.
Modification.